Hey guys, welcome back to my channel where we explore interesting math problems. Today, we'll be looking at a geometry problem on ratios and triangle similarity. So the question reads, the side length of the square shown on the left is 2 square root 15. E and F are the midpoints of AB and AD. DE intersects CF and CA at point G and H respectively. What is the area of triangle CGH? Since E and F are midpoints, let's first label them as half side length, which would be square root 15. From this, you can kind of guess that there might be some similarity involved. So let's first examine some angles and see where it leads us. So let angle DCF be red here. And now let's stop and notice for a moment. Triangle CDF has a right angle, a side length that's 2 square root 15, that's just the side length of the square, and a side length that's square root 15. And triangle DAE has a right angle, a side length that's 2 square root 15, and square root 15. By the Pythagorean's theorem, we know that they will have the same hypotenuse since they have the same two different legs, which means that triangle DCF and DAE are congruent triangles since all of their side lengths are equal. So if this angle is red, then this angle here must also be red. Now let's label angle DEA with green. And like before with the congruent triangles, if this angle is green, then this must also be green. And since they're congruent triangles, they would also have the same area. Now let's focus on triangle CDF. Notice that triangle CFA also have a base of square root 15, like CDF here, and a height that is equal to the side length of the square. This means that they have the same area. Since both triangle DAE and CFA have the same area as CDF, their areas must also be equal. And now let's break down these triangles. The area of CFA is the same as the sum of the areas of triangles CGH and the quadrilateral GFAH. And the area of DAE is the same as the sum of the areas of triangle DGF, quadrilateral GFAH, and triangle HAE. We can minus GFAH from both sides of the equation and simplify it down to this. And remember, triangle CGH is what we're looking for. So we can solve it by looking for the areas of DGF and HAE. First, to find the area of DGF, we need to notice another triangle similarity. Since triangle DGF has a red angle and a green angle, and triangle DAE also has a red angle and a green angle, they must be similar. Because the area for triangle DAE can be easily found because we have two side lengths and a right angle, if we know the ratio between these two triangles, we can find the area of triangle DGF. To find the ratio of the two triangles' area, we take the ratio of a corresponding side length, DF and DE, and square it because we're dealing with areas so it's two-dimensional. We already know the value of DF is equal to square root 15, but for DE, we have to use the Pythagorean's theorem to find it. Skipping over some steps, this is basically what you get for DE. Then simplifying, you get that the ratio is 1 over 5. Now we find the area of DAE. It's 1/2 times base square root 15 multiplied by height 2 square root 15. Simplifying, we get that the area is 15. Now back to this equation. We multiply both sides by DAE and get that the area of DGF is 1/5 of DAE. Plugging in, we get that the area of DGF is 3. Now we need to find the area of HAE. Like last time, we look for triangle similarities. These two red angles are the same because when you have two parallel lines and a line cutting through both of them, then this opposite angle is the same. And just as a side note, I'm using red like before, but they aren't the same red and green as last time. So this red angle and that red angle aren't actually the same equal red angle. Just keep that distinction in your mind so you don't get confused. Okay, and you use the same logic to know that both these green angles are the same. From this, you know that triangle HAE and HDC are similar since they have two pairs of congruent angles, which means that their third pair must also be congruent. Just to make the next step easier, let's label DC, which is 2 square root 15. And since the ratio of any two corresponding side lengths is the same, DH over HE is the same as DC over AE. Plugging in the known values, we know that the ratio is 2, which means when multiplying both sides of the equation by HE, we get that DH is twice of HE. It might be a bit confusing as to why this information is useful, but this is where you need a little insight. We already know that the area of DAE can be easily found, and that we're trying to find the area of HAE. And if you could mentally rotate triangle DAE so that the base is this hypotenuse DE instead, then the triangle HAE and DAE would have the same altitude. Like this blue line here would become the altitude instead if DE were to be the base. This means since they have the same height, altitude, the ratio of their areas would be the same as the ratio of their base. Because area is half times base times height, since there's no difference between height, you can eliminate it, and you can also ignore the 1/2 that they both have, then all that remains is the bases that's different. So to find this ratio in base, HE over DE, we break down DE into DH plus HE. Since DH is just 2HE from this equation, we can simplify the ratio down to 1 over 3. Since the ratio in base is equal to the ratio in areas, we can rewrite it in terms of the area. And from before, we know that the area of DAE is 15. So we can take this equation and multiply both sides by DAE, plug in values, and get that the area of HAE is 5. So back to our first and most important equation, the area of CGH is the sum of the areas of DGF and HAE. Plugging in the values that we found earlier, we get that the area is 8. And that is the final answer. Okay, that's it everyone. Thanks for watching and we'll see you next time.